going to look at energy and energy stores. We'll get straight into it. So first of all, we can see on the board we've got all of our different types of energy stores. Kinetic energy is to do with moving objects. So for example, if we have a car that moves, that has a high amount of kinetic energy store. Okay. Then we have elastic potential energy store. So if we have something that can be stretched, that would be our elastic potential energy store. Then we have gravitational potential energy store. So for example, if we have a building, so this is my building here, the higher up a person goes in the building, the more gravitational potential energy store that person would have. Then we have thermal energy, and thermal energy is to do with the internal energy of an object. So for example, if something has increased internal energy, it would get hotter. Then we have chemical energy, and chemical energy could be due to things like food, chemicals that we consume that then can be transferred into different types of energy, or it could be fuels, things such as batteries or petrol that you put into your car, etc. Then we have magnetic energy, and magnetic energy is to do with opposite ends of a magnet, so the North Pole and the South Pole, and where you have the North Pole and the South Pole coming together, they attract, and that's an attraction force, that's a pull. And where you try and put like poles together, so north and north or south and south, they push away from each other, and that's a repulsion force. Then the electrostatic potential energy store is very, very similar to magnetic. Apart from us having north and south poles, we have positive or negative charged particles that create the electrostatic potential there. Then we've got the nuclear energy store, and that is down to the things that go on within the nucleus of an atom. So where we've looked at chemical changes in the past, that's to do with electrons. Nuclear is to do with the nucleus of the atom. So those are our different energy stores. Energy cannot be created or destroyed. It can only be changed or transferred from one form to another. And the way in which energy can be transferred is there's four main ways: either by heating, or an electrical transfer, or the transfer can be mechanical, or it could be through radiation. Now, radiation will be covered in another session. However, we've got to remember radiation involves the electromagnetic spectrum. So radiation would also involve through light and sound. If we think about this, and these are the way that energies can be transferred from one store to another, the key thing that we had to think about was that energy is not created or destroyed. It's only changed or transferred from one form to another. So however much energy you start with is how much you would end with. So you don't start with more and then end with less, or start with less and end with more. So for example, if I start off with a certain amount of kinetic energy, some of that kinetic energy can be transferred into gravitational potential energy, but at the end of the day, altogether I still have the same amount that we started with. So looking at this as an example, if I have let's say I have a ball, and I take my ball into a building. Okay, so you've got your person holding a little ball there, and you take your ball into the building. The energy, as we're moving up the building, is being transferred into kinetic energy as we're moving up the building. When we get to the top of the building, then at the top of the building, the energy has been transferred into gravitational potential energy. If the ball is then dropped from the top of the building, the gravitational potential energy will then, as it's moving down, get transferred into the kinetic energy store. So we're not creating or destroying energy, we're just transferring energies from one store to another. Now, this quite often can come up as a question. So for example, if you've got something that starts some high up and it has gravitational, I'm going to put gravitational potential energy, I'm going to put GPE, short for gravitational potential energy, and energy is measured in joules. So if I say we start off with 1,000 joules of gravitational potential energy at the top, and then an object moves to part B where it has gravitational potential energy, and because it's still above ground level, so it's going to have gravitational potential energy and it has kinetic energy. And if I say at this point the kinetic energy is 700 joules, what is the gravitational potential energy? We've got to remember that energy cannot be created or destroyed. It's only being transferred from one energy store to another. So if 700 of the 1,000 is transferred into the kinetic energy store, then the 300 must still be the gravitational potential energy. So we can see that 300 joules and 700 joules adds up to the 1,000 joules. So we're not creating, we're not destroying, we're just transferring from one type of energy store to another. Now let's have a quick look at the equations that we would need to do with some of these energy stores. First of all, let's start off with kinetic energy. So kinetic energy is EK, and the equation we need to know is 1/2 mv squared. So energy is always measured in joules, mass is measured in kilograms, and velocity is measured in meters per second, and that's how quickly an object is moving. So that's the equation for kinetic energy. Make sure that you learn this. The second equation that we have to know is for elastic potential energy, and here the elastic potential energy is very similar to kinetic energy, is 1/2 ke squared. Again, energy is measured in joules. We have the spring constant, which would be measured in newtons per meter, and then we have the extension, which is a distance and is measured in meters. Then we've got the gravitational potential energy. So this equation is, now for this one we're going to put a P for the gravitational potential energy, and it is mgh. The gravitational potential energy, again, energy measured in joules, so all the energies are measured in joules. The mass is going to be measured in kilograms. Acceleration due to gravity is going to be measured, sorry, no, is not going to be measured, is 9.8 newtons per kilogram. And this gravity, this is for Earth. If you were on a different planet, then gravity would be different, but on Earth it is 9.8. Sometimes questions might ask you to use it as 10, which is fine, so look out for that in the question, but they usually tell you what they would want you to use gravity as. Height is, again, distance would be measured in meters. Thermal is usually measured as a change in internal energy, and this triangle is called delta, and that means change. So we have our change in energy, and that is measured with m, small c, and then delta, again change, theta. Theta denotes temperature. So change in internal energy is going to be measured in joules. M is the mass of the object that you're using, so that would be measured in kilograms. Now C is known as the specific heat capacity, and a specific heat capacity is the amount of energy required to increase the temperature of 1 kilogram of a substance by 1 degree Celsius. Okay, and that's called the specific heat capacity. So that is therefore measured in joules per kilogram degrees Celsius. And the theta is going, the delta is going with the theta. So delta theta means theta's temperature, so that means change in temperature. So this is change in temperature, and that's going to be measured in degrees Celsius. And you've got to be careful here, because change in temperature means you have to measure the initial temperature, the starting temperature, and the final temperature to be able to work out the change in temperature. The last part that we're just going to go over is we may want to know the rate at which energy is transferred. In other words, we want to know how quickly energy is transferred from one store to another, and that is known as power. And power is represented by a P, and we have two equations that we can use to work out power. So the first equation would be E divided by T, and P denotes power, so we're working out the power. E is energy transferred, and T is time taken. So energy transferred would be measured in joules, because it's a form of energy. Time taken is measured in seconds, and power is measured in watts, so a W for watts. Now 1 watt of energy is 1 joule of energy transferred per second. There is a second equation that we have for power. So power can also be written as W, which is work done, and work done and energy transferred are the same. So we can write power as work done divided by time taken. And it's just, you just need to look at the question that you're using to decide which one of these you are going to use. So again, W represents work done, T is still time taken, and P is power, and the units for these again is watts for power, joules for work done, and time taken is seconds. So that's all of our equations there. Okay, so now let's consider some questions. The first question, we have a rocket which has a mass of 5,500 and a speed of 700 meters per second. And we're going to work out the kinetic energy. So first of all, let's write down our equation. So kinetic energy is a half mv squared. Then we put our numbers in, so we're going to have a half, which is 0.5 times the mass, which is 5,500 kilograms, times the speed squared, so that would be 700 squared. And if we calculate that out, we get an answer of 1.35 times 10 to the power of 9. Now, if we have to convert that joules here into kilojoules, 1,000 joules are in a kilojoule, so we would divide our answer by 1,000 and we would end up with 1.35 times 10 to the power of 6 kilojoules. Now in this next question we have a high jumper who is going to have to raise his mass 1.4 meters high. His mass is 75 kilograms and the gravitational field strength is 10 newtons per kilogram. So the gravitational potential energy is mass times gravity times height. If we insert our numbers, we've got 75 kilograms as the mass, 10 newtons per kilogram as our gravitational field strength, and he's going to have to raise his mass 1.4 meters high. And if we calculate that out, we get an answer of 1,050 joules. If we were asked to change our answer into kilojoules, we would divide this by 1,000 and that would be 1.05 kilojoules. Now in this next question, we've got water falling and it's going to fall a distance of 20 meters. We are asked to calculate the potential energy of 1 kilogram of water at the top of the waterfall. So because it's raised, we're going to be looking at gravitational potential energy, which again is mass times gravity times height, and the mass is going to be for 1 kilogram of water. The gravitational field strength on Earth is 9.81 and the water is raised 20 meters, so it's going to fall 20 meters. Now if we work that out, we get an answer of 196.2 joules. Now quite often when we're working out gravitational potential energy, especially about things falling from a height to down below, there's usually a follow-on question and it says what will be the kinetic energy of the 1 kilogram of water just before it lands in the pool. So just at the bottom before it lands in the pool, how much kinetic energy would there be? Now here is when we've got to remember conservation of energy. So energy can be transferred from one energy store to another. Now we worked out that we're going to have 196.2 joules of energy as gravitational potential energy at the top, and then we're trying to work out how much kinetic energy we would have at the bottom. So all of this gravitational potential energy just before the water hits the bottom there will be changed into kinetic energy. We would have that transfer of energy going on. So we don't really need to do a calculation here. It's just for us to appreciate that energy is not created or destroyed. It's just transferred from one energy store to another. So the gravitational potential energy store is all transferred into the kinetic energy store just before the water hits the bottom there. And that's why it's only 1 mark. You're not actually calculating anything, you're just recalling conservation of energy. Now, with this next question, we have a 30-watt bulb uses 600 joules of electrical energy in a period of time. It produces 450 joules of light energy, and the rest of the energy is wasted. So we've started off with 600 joules. Calculate the energy wasted by the light bulb in this period of time. So if we started off with 600 and 450 of it was useful energy, whatever's left, so the 600 minus 450 joules, whatever is left is going to be our wasted energy. So that would therefore be 150 joules of energy is wasted. Now, what happens to the energy that is wasted in the light bulb? So all the wasted energy would usually be in the form of heat, and it's going to be dissipated or it's going to be transferred to the surroundings. Okay, now we've got to calculate the efficiency of the light bulb. So here we need to remember our equation for efficiency. So efficiency is the useful energy divided by the total energy. And if we work that out, the useful energy we know was 450 joules of light energy, divided by the total energy was 600 joules of energy. So 450 joules divided by 600 joules would be 0.75 as the efficiency. If we were giving it as a percentage, then we could do 0.75 times 100, and we could say it's 75% efficient. So either of these answers would be correct. Now, for this last question, how long would it take the 30-watt bulb to transfer 600 joules of energy? So how long would it take? Now, here we're going to use our equation where power equals the energy transferred divided by time taken. Now, if we rearrange this equation, we would have time taken equals energy transferred divided by power. So then to work out our time taken, we would do 600 joules of energy divided by the power, which is 30 watts. And if we work that out and we do 600 divided by 30 watts, we get an answer of 20 seconds. Now let's consider how we can reduce heat loss in our house. So first of all, let us have a look at our house. So here we have our house. We have our front door, we have our window, we have the upstairs, we have a radiator, a bed, and we've got cavity wall here. Now cavity wall means that you have a layer of wall, another layer of wall, and you can either have air in this area here, or sometimes you have it being filled in with foam. Okay, so that's just to show what the cavity wall is. Now, when we're looking at how to reduce heat transfer from our house, because once we get our house nice and warm, we want to keep it that way. We don't want the heat inside the house easily being transferred outside, because that would lose energy. And so one way is cavity walls. And they reduce heat transfer to the outside. Then we can also have loft insulation, so insulation that you have in the loft. And the loft insulation is made from insulating material. Again, they would help to reduce convection currents. Then we have our windows, and if your windows are double glazed, write that down there, double glazed, that works in the same way as the cavity walls, but instead of having 2 layers of brick, you have 2 layers of glass with a small air gap in between. The glass obviously reduces heat loss through conduction because it's an insulating material, and the small space here would help to reduce heat loss through convection. Then around your doors you can put draft excluders. I'll do that here. And these will help reduce heat loss through convection, because what happens is they fill the little gaps between the outside and the inside, and they're made from an insulating material, which means that heated air particles from inside your home would not be able to go outside, so it reduces heat transfer through convection. And those are the main ways in which you can help to keep your home warm.